In this video, I'm going to describe the dispersion of light, or the spreading of light into its spectrum of colors. So dispersion means to spread, and when we talk about the spectrum of colors, it means we're going to split up white light into all of the various components, the 7 colors that make up white light. Now, this is precisely the same principle that enables us to see rainbows when it rains. So, how does this work anyways? You see, visible light is part of the greater electromagnetic spectrum. And we know that the components of the electromagnetic spectrum are as follows. So you start off with radio waves, R mimics G, right? So radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and finally you've got the gamma rays. And as you go down the spectrum, of course, the frequency increases and the wavelength decreases. Now, within the visible light, you've got a subspectrum of colors in this case, right? In this subspectrum, you've got red, the red color right at the very top. So red has the smallest frequency and the greatest wavelength. And you've got all the different colors: orange, yellow, green, blue, indigo, and finally you've got violet, which has the highest frequency because it's lower down in the spectrum, in the electromagnetic spectrum, and it has the smallest wavelength as well. So visible light, which is part of the greater electromagnetic spectrum, can be split up or spread into all of these different colors that make up the colors of the rainbow, which are red, orange, yellow, green, blue, indigo, and violet. You can remember that using the acronym ROY-BIV. Some people remember it in the reverse order as VIB-GROY, whichever is easier for you. Right, now what happens is, now the way it works is, when white light, which is made up of all of these different colors overlapping onto each other. Now, the way it works is, white light, which is all of these 7 colors, red, orange, yellow, green, blue, indigo, and violet, overlapped on one onto the other. So when white light comes across now, the way it works is, when light travels from one medium to another. To be a bit more specific, when light travels from one optical density to another, it refracts, right? But now, the way it works is, when light travels from one optical density to another, it refracts, so it bends. But the catch is, when it bends, it doesn't bend by the same amount. So not all of the components, not all of the colors with their respective frequencies, of course, bend by the same amount, refract by the same amount. So in fact, what happens is, all of these different optical densities here, all of these different colors of light here, have their own refractive indices that determine the amount of bending. And as you go down the spectrum, as you go from red to orange to yellow to green to blue to indigo to violet, of course, so as you go down the spectrum, the value of the refractive index increases for that particular frequency. So because of that, when all of these different colors all together that make up that white light, so as that light approaches and strikes that now, the way it works is, when light encounters an optical density, when light encounters a change in optical density, it refracts or changes direction, bends, right? But here's the catch. Now, the way it works is, when light encounters a different optical density, it bends or refracts. But here's the catch. Not all of the different colors, meaning different frequencies of light, bend by the same amount. So each color corresponds to a different set of frequencies, and not all of the colors bend by the same amount. In fact, as you go down the spectrum, as the frequency increases, the refractive index increases as well. So what that means is, as you go down the spectrum, so from red to orange to yellow, all the way through to violet, well, the amount of bending is going to increase as well. The amount of refraction is going to increase as well. And what that results in is, for instance, if white light encounters this prism, it's going to refract, but red is going to refract differently from violet. Red is going to refract a whole lot lesser than violet. It is going to refract, but not as much. So red refracts, but not as much as violet does. So with violet, you've got a whole lot, you've got a much greater refraction, which causes the white light to spread out into all of its different colors, all the way from red to orange, yellow, green, blue, indigo, and violet. Okay? So you might be inclined to ask, well, hang on, if that were the case, why doesn't that happen when we use a rectangular glass block? Why does it only happen when we use a prism or with a raindrop, for example? Well, the answer is, it does happen. So when white light enters this glass block, it does spread out into its different colors, because each of those different colors, from red to violet, has a different value of refractive index. And as you go down those frequencies, as the frequency increases, as you go from red to violet, the value of the refractive index increases, and so the bending increases as well. But in this case, when light emerges at the other end, it refracts back to overlap one. So all of the colors refract back by their respective amounts, so they start overlapping each other again, and so you've got white light again. Okay? So I'm going to show you a demonstration of the dispersion of light. So we conduct the experiment in a darkened environment. Ideally, it would have been a dark room, but anyways. So we've got a rain box. We've got a single slitted filter to create that beam of light, that single ray of light. Of course, the ray of light, that white light, is shown directly into this prism, and as the rays of light enter that prism, they refract, their respective colors, their components refract by different amounts, because each of those colors has a different refractive index, and so those colors spread out into a spectrum of colors, which is barely visible after the first refraction. However, I've used a second prism to further spread out those rays of light, and here you've got all the colors of the rainbow. See? So you see how white light has entered this prism and spread out into its 7 different colors according to their frequencies, and of course with those frequencies you've got those refractive indices, and then it gets further spread out by the second prism until you get this rainbow. Right? Now, rainbows are also formed using the same principle. So, for example, a ray of light that now, rainbows are also formed using the same principle. So, for example, a ray of white light comes from the sun and strikes the surface of a raindrop. Okay? And as it strikes the surface of that raindrop, the light refracts or bends due to the change in optical density. Right? So, water is more optically dense than air. So, we already know, we've already seen how light, or the individual colours of light, refract by different amounts according to their different optical densities, right? So each colour of light has a different optical, Now the same principle can be used to describe how a rainbow is produced. Now the same principle can be used to describe how rainbows are produced by raindrops. A single straight ray of white light encounters a raindrop, okay? And because it encounters the raindrop at an angle of incidence, at an angle of incidence that's greater than 0, and because the optical density of the water droplet is different from the optical density of air, so the light is going to refract as it enters the raindrop. Now, the amount of refraction isn't going to remain the same for all the different colours of light. So, according to their different frequencies, so the different colours are going to refract by different amounts with their respective refractive indices. So, again, red light is going to refract the least, and violet is going to refract the most. But in this case, something special happens. So, for example, red light refracts a little bit as it enters the raindrop. At the other end, so it refracts a little bit, so it bends a little as it enters the raindrop. As it reaches the other side of the raindrop, something special happens. The angle of incidence in this case happens to be greater than the critical angle of light in water. Right? We've already seen how to determine the critical angle. We know what it is, and we know how to calculate it. So in this case, because the angle of incidence is greater than the critical angle, and because light is traveling from an optically dense medium to a relatively less dense medium, so in this case, light won't refract out of the droplet. Instead, it will reflect. It will totally internally reflect inside the droplet. And then light would refract out of the droplet as it exits the water droplet. Now, that was for the red light, right? So you've got a certain amount of bending with the red light. You've got a certain amount of refraction with the red light. Let's see what happens with the violet light. So violet has a much higher refractive index. What that means is violet is going to refract a whole lot more than red. So violet refracts a whole lot more than red. And again, the angle of incidence of this violet ray is again greater than the critical angle of light in water. And because light is traveling from an optically denser medium to a less dense medium, with that condition, light will totally internally reflect again. So light will totally internally reflect again. And as that ray of light exits the rain droplet, it's going to bend again, it's going to refract again. This is how you've got all of the different colours of the rainbow spread out by a water droplet. Thanks for watching.